Okay. So, let us now, as I said, start counting the number of states, and we are after something called the density of states, and from there we will calculate certain physical properties of the system. For example, we can calculate the Fermi velocity, the Fermi momentum, Fermi energy, number of particles. So, those are number of electrons and so on, density of electrons. So, let us just start doing it. Now, we just showed that in a volume omega k in k space, you have V times omega k times divided by 2 pi cube number of states. So, then in a volume of a sphere which is 4/3 pi k cube up to a momentum k, the number of states is V omega k. So, this omega k I do not require, omega k is replaced by this by 2 pi cube. So, that is the in a volume 4/3 pi k cube, the number of states is this into 4 by 3 pi k cube, number of states, allowed k values, which is basically the states k values. So, this is the number of states inside a sphere of radius k is just this 4/3 pi. So, number of states. So, let me call number of k states represented by n sub k 4/3 pi k cube into V by 2 pi cube. Okay. So, this gives me k cube into V by 6 pi square. So, that is the number of k values that are allowed into the so 4, 2, 6, yeah, this is k cube V by 6 pi square. Now, this so inside the radius of k f, then inside a sphere of radius k f, k f, then the number of states n k f is equal to k f cube into V by 6 pi square. So, these many allowed k values are there in this state. Now, the interesting thing is that the electrons are spin half fermions. So, there are two spin states, spin projections allowed in each state, right. So, I can put at most 2 electrons in each of these k states. So, each allowed k value actually accommodates 2 spin states, 2 electrons spin. So, if you also count the spin, then let us call these as levels. So, the number of levels then is n equal to 2 times this number that we just calculated, k f cube by 6 pi square into V. So, that is k f cube V by 3 pi square. So, number of levels in that volume. of K space. So, correspondingly this E f is h cross square K f square by twice m, P f equal to h cross K f, then the Fermi velocity V f is equal to P f by m, which is h cross K f by m. Okay. Now, if you remember your classical velocities, this velocity is about 10 to the power 8 centimeter per second, okay, typically. So, if you remember your classical situation where the corresponding velocity there was the thermal velocity. So, I am just writing it thermal, which we obtained from this relation that half m v square thermal is equal to 3 by 2 k b. So, that gives so root over 3 k b by m, square root 3 k b by m is the thermal velocity, which is much smaller compared to this velocity. This is a fairly high velocity, nearly a 1/100th of the velocity of light, speed of light. So, this velocity is very large, and simply because you have to fill up states from the bottom and you can't put more than 2 electrons at the lowest energy level, lowest at any k value, and so you have to go on up in momentum states, and their energies are going up. And you actually can see that if you calculate this E f in a typical metal, it can be anywhere between half an electron volt to 15 electron volt. It is so large. Now, if you convert that to temperature, for example, 15 electron volt will be like 15 each electron volt gives you 10,000 degree Kelvin, 11,000 degree Kelvin. So, you can imagine what energies we are talking about now. So, and that is simply because of the fact that the Pauli principle prevented us from putting electrons, as many as electrons as we want at the lowest energy state. We had to go up. 2 is the maximum that you could do for spin half fermion. Okay. Okay, so let me just calculate something that is very useful. Now, since n within a volume within a radius of k, in a sphere of radius k, there are k cube v by 3 pi square number of states. I can write this as 3 pi square into k is h. Now, we know that h cross square k square by twice m equal to E. So, this basically 2 m E by h cross square. Okay. So, that is the to the power. So, that is cube. So, I have to take a cube of that. Okay. So, now what I can calculate easily is this number d n l d E, and this will give me a number which is 3 by 2 v by 3 pi square into 2 m by h cross square to the power 3 by 2 into e to the power half. Okay. So, that is the number of, you can simplify it, and but the important thing is that the density of this, so this is the number of levels available between two energies E and E plus d E, and this goes as e to the power half. So, that is a very important relation, that in 3 dimension for a quadratic spectrum the energy, the density of states goes as e to the power half root over of e. Now, the interesting thing is that if you look at this, the number of, if I take my k up to or e up to E f, then this n l up to k f is actually the same as the number of electrons. Because I have put in 2 electrons in each of these occupied k states, each of these k states that I am going to occupy, and then that is the total number of electrons. So, the number of levels gives me the number of electrons. This factor of 2 comes when you count the number of levels, number of states you do not count the 2, but then you multiply by 2 to get the number of levels, which is the same as the number of electrons. So, from that you can actually figure out that the density is n by V is equal to k f cube by 3 pi square, that V is gone. Okay. Okay. Now, another interesting relation you can find out is that n up to an energy E, is as we just mentioned, is V by 3 pi square into 2 m E by h cross square to the power 3 by 2. So, you are feeling your highest field level is at E, or you are counting the number of electrons up to an energy E. So, that is basically this, and then what you can do is take log on both sides, log of n of E equal to whatever comes here, you do not bother, is 3 by 2 log of E plus constant. These are all constant terms, h cross square m V 3 pi square. Now, take a just derivative. So, d n by n is equal to 3 by 2 d E by E. So, that means d n by d E equal to 3 by 2 n by E. This is a very useful relation. I mean, this is the same, this relation is also, this tells you the number of electrons up to an, so the so in this is basically again the density of states, number of states between E and E plus d E, and that is that is now expressed in terms of n and E. Now, you can bring your n and E from the previous expression, and E by n can be calculated using other quantities like E f, k f and so on. Okay. So, let me see what we want to do now is that if once we have the volume of the in the k space and the density of states, we can calculate the certain quantities. For example, we can calculate the total energy. How much is the total energy? It is basically h cross square k square by twice m sum over k up to k f, right, and then of course multiply by the spin degeneracy. So, that is what we want to calculate, and then I will show you where this density of states can become useful. So, let us just take any function of k, f of k, and we want a summation, right. So, this is basically the same as f k into delta k if delta k is a volume in the k space, then what? So, this is an identity, because the number of states inside the volume delta k are basically these, delta k divided by 2 pi by L cube, which is V by 2 pi cube. So, now take limit V going to very large, which means delta k is very small. So, delta k going to 0 limit, and then you can just write this as f sum over f k equal to f k delta k V by 2 pi cube equal to d k. So, d 3 k by 2 pi cube into V to f of k. Okay. So, this can be converted to an integral now. So, to calculate this, now I can use this one. Instead of a summation over all the k states, I have to keep counting the k values, all these separate. I will not do that, because that is too tedious, and that is not possible that in some situations. And so, I will just take the density of states, and I know how many density of states lie in a interval k and k plus d k, and that is what we just do. So, it is exactly what I just did. So, then that means 2 times k less than k f h cross square k f square by twice m equal to V integral 0 to k f h cross square k square by twice m into that volume element divided by 8 pi cube. So, so counting states is actually quite useful. Now, I am what I have done is that I have just replaced the sum by an integral over a volume in k space, and that volume contains how many k values I know. So, that is what I have just done, and this basically is the result. And now, d 3 k is k squared d k. So, 4 pi k squared d k, I will put that in, and at the end of the day you will find there is this factor of 2 for spin degeneracies. So, I will calculate this. You can go ahead and calculate it, and you will find that this is 1 by pi square h cross square k f square by 10 m into V. Now, we also know that n is equal to k f cube by 3 pi square into V, then it is easy to show that E by n from these two relations is equal to 3 by 5 h cross square k f square by twice m equal to 3 by 5 E f. So, this is a very useful relation. This tells you the energy per particle on an average energy per particle is like 3/5 of the Fermi energy of the system. So, let me recap what I did. So, what I did is that I calculated the first. Let me just go back to some slides and look at this slide. So, this is what I actually did. this is this K space. Okay. Now, in this K space the occupied states look like a sphere, as I said. So, this is the sphere that you can see the sphere. This sphere is now opened, this sphere has been opened up, and one-eighth of it is shown, and you can see that these dots, these green dots are your K states, and these circles, small green circles or these dots are the allowed K values. Each of these allowed K values are filled up by 2 electrons, they are occupied by 2 electrons. So, you keep on increasing it, and then you just complete your filling, and all the n electrons are now occupying some K state starting from the lowest one, and then the sphere that you obtain is the Fermi sphere. So, this is the sphere in the K space that is the last occupied surface, and that is, as I said, is called the Fermi surface. It separates the unoccupied states are outside this sphere, occupied states are inside the sphere. So, that is the sphere of last occupancy. It separates the unoccupied from the occupied, and it is now this on the side is a bigger picture. This one shows that this one, for example, these are shown how you actually put each of these green circles contain these. So, for example, these green circles contain 2 electrons each, and if you want to excite an electron from this state, this ground state, the ground state was where every one was filled up, every state was allowed K values were filled up by 2 electrons each. To excite, now all you have to do is to take an electron outside this surface, because inside the surface every state is filled up, outside the surface there are states which are empty. So, to generate an excitation of this system, you have to take an electron and then take it outside the sphere. As you can see, the last electrons which are at EF, they are or at the Fermi surface, for them the amount of energy required to excite is exceedingly small, but the ones which are deep down somewhere in the down here, for them you have to give this much of energy to pull them out of the Fermi surface. So, this from here to here, that much of energy is required if you want to pull out an electron from here, but for an electron close to the Fermi level or at the Fermi level, you require almost 0 energy to excite. Okay. That is a very important concept in the theory of electrons, and so this kind of pictures will emerge at every stage. For example, if I want to calculate the specific heat, what do? I give some heat energy and then try to see which are the electrons which take the energy and how much energy is taken. Suppose I give a small amount of energy, then only these states will be excited. If I want to excite a state from here, I have to give huge amount of energy. So, that is the kind of physics that we will discuss in the next class, but this is a beautiful illustration of how to count the states and put the electrons in the respective states starting from 0, from the lowest energy state and fill up a so called Fermi surface, so Fermi volume, and fill up all the states below the Fermi surface to get the ground state, and then the excitations are just almost 0 energy is required to excite an electron sitting at the Fermi surface to go to a state which is just higher than the Fermi surface, which is unoccupied. So, for example, if you look at this view graph, then there are density of states shown here for different real systems, different systems. For example, this as I said, this blue curve, as you can see, is the square root, it goes as square root of energy. So, this is for the 3-dimensional case I just worked out. Now, I leave it as a problem for you to work. What happens when you have a 2-dimensional system? You will see that in 2 dimension the density of states will become the independent of energy. So, it has no dependence on energy, and that is something that you should be able to calculate, because now you have a surface rather than a volume, and in this volume you will be able to calculate the the density of states, which will turn out to be energy independent. It is just a constant. It is basically m by pi h cross square. In one dimension something happens. In one dimension, as you can see that these are like these spikes, and so these are so these spikes are like they come down as this is the density of states. So, these spikes are different energy states. At each energy states, between two energy states, the energy dependence of the density of states is 1 over root omega. So, e to the power minus half, and that is interesting because that has a singularity at energy going to 0. So, it diverges as E goes to 0, and that has a strong effect in many one dimensional systems. Many physical phenomena in one dimension reflect this strong singularity of the is not a strong singularity, but it is a singularity in the density of state. So, that is reflected in many of the properties. This is quantum dot, basically 0 dimensional object. Here of course, there are only energy levels, and these energy levels are basically represented by this kind of delta function kind of line, just a single line at a particular energy. So, that is the density of states for a 0 dimensional object, which is basically quantum dot. In general, the density of states, if you calculate the way I just did, you will find that the calculation will give you the density of states as and in d rho of, suppose I write this as rho of E, which is basically d n d E in a dimension d, typically goes as e to the power d by 2 minus 1 when E goes as k square. So, this relation basically is what I just showed you, that in 3D d equal to 3, this is e to the power half, d equal to 2, this is e to the power 0, that means independent of energy, d equal to 1, it is e to the power half minus 1. So, 1 by 2 minus 1, which is minus half. So, this is like square root the 3D, 2D is a constant, and that step like structure I was showing was basically for different bands. There are different steps, different these straight regions. So, this is 2D, is rho E versus E, rho E versus E, and in 1D of course, there is a huge pile up of density of states I equal to 0, and it goes as 1 by square root of E. So, this density of states, see the 3 dimension is the most well behaved density of states. As you go up in the energy, it sort of becomes nearly constant. 2 dimension is just constant, nothing happens here, but 1 dimension has this 1 over E to the power half dependence, which causes important effect, which we will discuss at some point in the future. 0 dimension of course is so this is 1D, and 0 dimension is of course the levels, they are just levels at those energies, corresponding allowed energies, and that is how the density of state looks like. Okay. So, we will discuss the consequences of all of these at suitable point. We will stick to 3 dimension systems for the time being, and when time comes we will discuss 3D, 2D or lower dimension systems. For now, as a homework, you can work out for the 2D with this kind of a spectrum E versus k square. Okay. Thank you so much.